Before we start with today's topic, I would like to say that I made a mistake in the previous lecture. In the denominator, I had written h cross square, but it's actually h square. So please correct that mistake before you jump into today's lecture. Thank you. So here in this equation, if you can see, this one over here is nothing but the delta function. And this one, which is TMI, transition momentum integral, and this one is the constant. So the delta function can be written as del of x is equal to limit n tends to infinity 1 by 2 pi sine nx by 2 divided by n by 2. Here instead of x it's delta omega. Del of delta omega is equal to limit n tends to infinity 1 by 2 pi sine n del omega divided by 2 the whole divided by 2. Okay, I guess this is not one second, this is x not n. Okay, fine. Yep. So now what you have to do is you just have to substitute this back to that equation. Instead of that del omega minus omega phi minus omega, you have to write this formula. So you'll get it as pf of t is equal to the rest of the terms. You have to rewrite it. Okay. So it was square term, so you just have to square it and cancel the terms which is there repeating. So you'll get it as pi square e naught square by h square omega fi divided by omega the whole square. So the previous lecture I made a slight mistake. I think I wrote this as h cross, but in the video it is not h cross. Actually I meant to say that h cross is equal to h by 2 pi, but accidentally I wrote it as h cross here. Please correct it. Okay. Yep. So continuing with this equation, sine n del omega by 2 the whole divided by omega by 2 square. Okay, so here if you can see, the transition momentum integral is modulated by the sinc function. Okay, sinc function. Okay, so we can write it as this thing is equal to t square. Okay, so this one over here you can write it as modulating function, and this one, as I said before, it is EMI. And if you plot the modulation function versus the delta omega, so it's like this: del omega versus sine square del omega by 2 the whole divided by omega by 2 the whole square. So this is 0. Oh wait, okay, this is 0 1 2 3 is 2 minus 3. Okay, so if you can see, there will be small bumps here, and at 0 there will be a really big peak. Okay. Okay. So this is how the graph looks like. So this peak one, the peak over here, is called the resonance condition. And you can also see that there are tiny absorptions even in the wings. And the wings are governed by the equation over here, sine square del omega by 2 the whole square divided by, sine square del omega by 2 divided by del omega by 2 the whole square. So the resonance condition is like this: omega fi is equal to omega. So that's the reason why del omega is 0, because omega fi and omega is equal to same. And this condition is also called as Bohr's condition. Okay, Bohr's condition. So from here you have to note few points. That is, omega is a variable quantity. It varies with incident light and all. So that's the reason why it can vary the sinc function. It is very clear that absorption takes place even in areas without resonance, but they are very feeble, so it's okay. And then the maximum probability of resonance happens at omega is equal to omega fi, which I said that is nothing but the Bohr's condition, and that means delta omega is equal to 0. Okay, so P of t becomes pi square e naught square by h square omega fi divided by omega the whole square sine square del omega by 2 whole divided by del omega by 2 the whole square, and then this one. Okay, so this is the TMI. Okay, so this over here, this term tells you about the intensity. This term line width, and this one is the selection rule. Okay, so this is the probability of transition from initial state I to a final state F. Okay, so it's from I to F, and if you see, it is time dependent. As long as perturbation is there, transition will also take place. So longer the perturbation, longer will be the transition probability. So now there's one issue that we will look in this lecture. From initial state I, which is precisely defined, to final state F, which is also precisely defined. So we can say that H naught of I is equal to E1 initial of I. Here it is H naught of F, EF of F. Okay. But this is valid when delta F is separated out. That means F is a clean state that does not have anything in its vicinity. But that may not be possible all the time. So what if F lies in the midst of some states? So let us look at the possibility that there is an initial state I, which is ground state, which is well separated, but there is final state F, which is between many such states. So we can say a state F is embedded in a density. It is not cleanly separated state, but state F is embedded. And here you can think of an hydrogen atom. Main motive is that we have to find P of T, where the final state is not just one state but many states. So we can write the equation like this: T is equal to rho E dE, where this is nothing but density of states. Okay, right. Density of state means for a unit energy how many energy levels are packed. Okay, now what you're going to do is you just have to substitute the values Pf of T back to here and then multiply. Okay, so I'll just copy this equation to there and solve it. So there's an integral over here, and I can write rho f of A here. Okay, there's a dE as well, dE. Okay, fine. For very narrow range of energy, change in wave function is minimal and can be ignored, as I said before. So here this thing will be constant because wave function in average sense is defined. In order to evaluate this integral, let us assume that delta omega T by 2 is equal to x. Okay, delta omega is omega Fi minus omega. Omega Fi is nothing but E by h cross. Okay, so I'm just substituting. So del omega, I'll open the bracket and I'll write like this, by 2 T is equal to x, 1 by 2 common. Omega Fi is nothing but E by h cross minus omega T is equal to x. Now to take dE of it, so dE is nothing but dE by 2h cross T dx. So dE is 2h cross by T dx. Fine. So you will make this. So dx is dE by 2h cross T. Fine. So we'll just substitute. We'll get it as pi square E naught square by h square. You just have to substitute it. Okay, I missed a T here. I'm sorry, there's a T there. Yes, there's a T here. Okay, I've been missing a T since I don't know how long. Okay, oh yeah. Sorry. This N over here is the T for us. Okay, yeah. So since here I'm missing T, so please check this again and write T. Okay, there's a T, right? Okay, so simple substitution: sine square x by T square x square, then rho f of e, this should come outside the integral. I'll just rearrange 2h cross by t dx, right? And then the TMI, you have to rewrite the TMI. So okay, now this t and this t cancels and you'll get this equation to be like this: 2h cross t dx and the TMI. Okay, this integral over here is valid for a bunch of energy levels around ket f, which will not even vary if we change the limit from minus infinity to plus infinity. So instead of this one, I will write it as minus infinity to plus infinity, because it doesn't change, because we are simply adding zeros above and below the bunch of states where the wave functions varies. So it's fine. And then you can see that this thing over here, integral, this thing is nothing but pi. Okay, there's a dx also, include that also. Exclude the 2h cross by t, this part over here is nothing but pi. So you can rewrite the equation to be like this: h by 2 pi, and on substitution, let's see what happens. And then again, I don't know why we are doing this, but we are doing this. H cross is equal to h by 2 pi. So h is equal to 2h cross 2 pi h cross. Just substitute that, you will get the final equation to be like this. So this is what you finally get. You can cancel off the pi, and yeah, this is how you finally get. Okay. Oh yeah, before that there is a mistake which I have caused, so I can clarify now itself. So here this is t square 2h cross by t dx, right? So t should not, it's not in the denominator, it should be in the numerator. So that's the mistake which I made. So please correct that one. I just realized it now. So the t in the denominator should be in the numerator. Okay. Next, what you're going to do is, so there's something called the rate of absorption, that is omega fi. So by definition, it is 2 pi h cross nu square rho f of E, and this thing over here is nothing but E naught square by 4h cross the TMI square omega fi by omega the whole square. So it's by definition, it seems. We don't have a proof for this. I can define something called rate of absorption omega fi. By definition, it is 2 pi h cross mod of mu square rho f E, and modulus mu square is nothing but E naught square by 4 h cross square transition moment integral omega fi by omega the whole square. Okay, so this is called the transition dipole. So the terms inside this transition dipole equation is constant, therefore this term is also constant. So we can say that omega fi is equal to k. Okay, these things are constant, so we can take it as k, and then the left out term is rho f of E. So we can say that from ground state to final states, rate of absorption, that is omega fi, depends on density of states. Okay, so this is rate of absorption. If I didn't mention earlier, please take a note on it. So we can conclude by saying the rate of absorption is proportion, it depends on density of states, and hence this is called Fermi's golden rule. omega Fi proportional to rho f of E, or omega Fi is proportional to mu square. That's it for today. In the next video, we'll be talking about rotational spectroscopy. Thank you.